Kinematics of general plane motion. Let's start with the definition of a rigid body. Rigid body is a body on which the distance between 2 points do not change during motion. So a solid body is generally a rigid body. So while performing a planar motion, the motion of one point with respect to another can only be a circular motion. So if I'll sit at one point, let's say A, point 1 and 2 will appear to move around A in circles in radius r1 and r2 respectively, with the same angular velocity, which is the angular velocity of the body. So in this example, there are 2 points 1 and 2 on the rigid body. A is also a point on the rigid body whose velocity is known to us, and angular velocity of the body, again I am using the term angular velocity of the body, is given, and we have to find the velocity of point 1 and 2. So in these two diagrams, velocity of point 1 can be given as velocity of A, and when we vectorially add with velocity of point 1 respect to A. So in these diagram I have shown the velocities of 1 and 2 with respect to A, and these are the velocities of A. When we superimpose these two motions, one is pure translational, we'll talk about this more, another is pure rotational, we get the velocity, absolute velocity of point 1. As they are opposite, so I'll put a negative sign at this place. So if we have to find out V2, VA plus velocity of 2 with respect to A, now they are in I and j cap now, so we have to add them vectorially. Similarly, in the next example, we have to find out the velocity of point 1, 2, 3, 4, 5, whereas the velocity of center is known to us and angular velocity of the body is known to us. So again we gave VC to all the points, pure translational motion, and we fix the center and rotate it with the angular velocity of the body. So by mistake just shown this arrow in reverse direction, it should be clockwise. So r omega are the velocities with respect to center in the respective positions. Velocity of point 1, VC from this diagram, r omega from this diagram in the same direction, so we'll add 2 VC from this, r omega opposite to that, so minus VC minus r omega. Similarly for 3, we have to vectorially add them, so the speed will be VC square r omega square under the root, and for 5 we have to take the components in I and j. So VC plus r omega sine theta I cap and r omega cos theta minus j cap. So in these diagrams we'll find out the acceleration of point 1, 2, 3, 4, whereas the acceleration of center and its velocity and angular velocity, angular acceleration of the body are known to us. So this is a translatory diagram in which all the points are having the same acceleration. This is rotational motion about its fixed center, though the center is not fixed, and center is, I'm not saying that the center is the axis of rotation, but because we know the velocity of center and we gave the velocity and acceleration of the center as translatory terms, so in this diagram we have to keep the center at rest. So in this diagram I have shown centripetal acceleration and tangential acceleration of all the points. When we'll superimpose or vectorially add these vectors, we'll get the desired acceleration as written in this page. In this diagram we have to find the relation between velocity of circle and plank, so that no slipping takes place at the point of contact. That can be termed as pure rolling, where no slipping takes place, and we have to find the speed of these points if plank is at rest. So for no slipping, velocity of all the points in contact should be same, so v1 should be equal to vp, and by superimposing those two diagrams, when we find out the velocity of point 1, we get its vc minus r omega, so it should be equal to vp. This is the relation, and if we put vp equal to 0, we get vc equal to r omega, so the bottommost point will be at rest now. The topmost point will be moving with twice the velocity of the center, whereas 2 and 4 will have a speed root 2 times the velocity of the center. And the bottommost point is known as instantaneous axis of rotation. Any point on the body which is instantly at rest is the instantaneous axis of rotation, or is on the axis of rotation. Pure translation motion, it's quite good definition. When all the points on the rigid body have same velocity and acceleration at an instant, at that instant the body is in pure translational motion. And pure rotational motion, and all the points on the moving body are moving circles with same angular velocity. And these are few important things about axis of rotation or center of rotation. Velocity of any point is perpendicular to axis of rotation because they are moving in circles centered at axis. The perpendicular distance of the point is r, radius of the circle in which it is moving, so its speed will be r omega. And axis of rotation, AOR, passes through a point having 0 speed on the rigid body, if any. That means axis of rotation may or may not lie on the body. In this diagram there are 2 points 1 and 2 whose velocities are shown to us, and we have to find the axis of rotation of the body. So what I did, I draw the perpendicular on these velocities vectors, and where the perpendicular intersect, at that point the axis of rotation will be. So in this diagram here it should be, and if there are 2 points on the body 1 and 2 which have parallel velocities, let's say v1 is greater than v2, so if the point is nearer to axis, its speed will be less. So as v2 is less, point 2 will be nearer to axis, and we take the distance to be x, and assuming omega is the angular velocity, so we can just predict that omega has to be clockwise because this is the axis of rotation, and if you rotate clockwise, these 2 points will get the velocity in downward direction. So by assuming omega, we get v2 as x omega and v1 as x plus l times omega, and by taking the difference divided by l, this is a very important formula for calculating angular velocity directly. Difference of the component which are perpendicular to the line joining them divided by the separation, and from these two equations we can also calculate x. Man is pushing a plank which is placed on a cylinder or sphere of radius r, and the separation at that moment between man and sphere was L. So there is no slipping anywhere. There is no slipping at this point between plank and sphere, and at the bottom also. So we can say that velocity of the center or velocity of the sphere is half the velocity of the topmost point. We solved this earlier. So if the man is moving or the plank is moving with v, center will be moving with v by 2. So the relative velocity between them will be v by 2, and the separation is decreasing at that rate. So the time taken will be L divided by v by 2, and the distance moved by man will be, it is moving with speed v for this much time, 2L by v. So when we multiply time by speed, we get the man moved a distance 2L and the sphere moved a distance L. In this diagram we have to find the velocity of the center in terms of v and omega. So in fact we have to find the omega also, where the information giving is no slipping taking place at any of the position, means there is no slipping here and there is no slipping here also. And by applying the same definition, difference in the velocities perpendicular to the line joining them, so as they are already in opposite direction, their difference will be 6v divided by the separation, which is 2r. So we get omega as 3v by r. And by applying the same superimposition method, velocity at the top will be vc plus r omega. So we write 4v is equal to vc plus r omega. We already have omega, so we get vc as v. And if we'll talk about these examples, this is a circular disc or a cylinder which is allowed to roll, and this point is attached to a string which is fixed at the support. So we can say if the sphere is moving downwards with an acceleration a and rotating with an angular acceleration alpha, the point 1 has an tangential acceleration which is equal to a1 ac plus r alpha. Again, similar superimposition of normal translatory and rotatory tangential acceleration. And these acceleration we try to neglect the centripetal acceleration, because we are interested in calculating the acceleration of block which is moving vertically down only. So AB will be equal to A1, no slipping taking place here also. And this diagram, AO will be 0 because it's fixed. So by assuming AC is the acceleration and alpha, so AC will be downward and R alpha will be upward, so they will cancel each other, and this will be R2 alpha in fact. So AC equal to R2 alpha, and if we calculate acceleration of this point, that will be AC downward and R1 alpha also downward. So we'll add them to get this. We have to find the relation between these parameters if point 1 and 2 are on the same rigid body. So if these points are on the same rigid body, the separation between them, or we can say, will be constant, or in other words we can say that the velocities along the line joining them has to be same. So v1 cos theta 1 is equal to v2 cos theta 2, and assuming that someone v1 sin theta 1 is greater than v2 sin theta 2, so the rod will appear, this point will move faster upward and this point will move upward with a slower rate. So the rod will appear to rotate anti-clockwise. So we'll take the same formula, difference in the velocities perpendicular to the line joining them divided by the separation between them, to get the value of angular velocity. If our assumption is wrong, we get angular velocity in clockwise direction, or we get negative angular velocity in anti-clockwise direction, which are the same terms. Okay, thank you.